let's take a look at this. So we've got differentials now. We have the increment theorem. So I want to just run through an example in which we compute the differentials, we compute the delta y, and we go through and find the epsilon that makes the increment theorem valid. So the function we'll investigate here is y equals 1 over 2x. And we'll let delta x, right, be an infinitesimal. And so first we're going to compute what the change in y is. So delta y would be 1 over 2 times the quantity x plus delta x minus 1 over 2 over x. Now this rational expression, we're going to simplify this. And so this is equal to 2x minus quantity, and I'll distribute this 2 through, 2x plus delta x, all divided by, well, we're going to end up with a 4x times x plus delta x. Doing a little simplification, we get that this is negative, whoops, I did forget to distribute my 2 there. Sorry about that. Negative 2 delta x divided by, and I'll distribute this through, 4x squared plus 4x delta x. So just doing algebra, that computes our delta y. Now, by the increment theorem, this delta y should be equal to, let's scroll this up, increment theorem, delta y should be equal to f prime of x, delta x, plus some epsilon delta x. So let's go through and we'll compute what f prime of is. From that, we'll be able to compute what the differential of y is. So f prime of x, remember this is our delta y. So f prime of x, by definition, is the standard part of change in y over change in x, which is equal to the standard part of, so we'll put this in, negative 2 delta x divided by 4x squared plus 4x delta x. And that whole thing divided by delta x, which is the standard part of negative 2 delta x divided by 4x squared plus 4x delta x times 1 over delta x. And of course, we get cancellation here, and I've got 2 that can cancel there. And so this ends up being equal to the standard part of negative 1 all over 2x squared plus 2x delta x. And now this is not an indeterminate form. The top is finite, as is the bottom, since x is real and delta x is an infinitesimal. When we slide the standard part through, the numerator will be negative 1. This will be 2x squared, and because of the product here, this standard part of this is 0. So we get left that the derivative is equal to negative 1 divided by 2x squared. So that's what f prime is. And so we can formally say that dy, which we know by definition is f prime of x dx, and filling in what f prime is, this is negative 1 over 2x squared dx. That's our differential of y. Differential of y is f prime dx. F prime we just calculated is negative 1 over 2x squared. And so the differential of y is negative 1 over 2x squared dx. Okay, so we have up here, though, our increment theorem says that we should have some agreement in that delta y, this expression here, should be equal to, so delta y should be equal to f prime of x dx, or delta x, plus some epsilon delta x. So we will set up our formula. We can just use this equation here. And right, so we, by the increment theorem, it says that delta y should be equal to f prime of x delta x plus some epsilon times delta x. Replacing this, we know that delta y is equal to negative 2 delta x divided by 4x squared plus 4x delta x. That's what our delta y is. This needs to be equal to, so f prime of x dx, so f prime of x is negative 1 over 2x squared delta x plus some epsilon times delta x. And so what we need to do now is solve for this epsilon. We want to know what is the epsilon that makes this true. And that's now just a straightforward algebraic move. So I'm going to divide through by delta x. Now I've got a delta x here, a delta x there, and a delta x in the numerator. So this tells me that negative 2 over 4x squared plus 4x delta x is equal to negative 1 over 2x squared plus epsilon. And now solving for epsilon, we can bring that over and we get that epsilon is equal to 1 over 2x squared minus 2. Actually, I'm going to do something real quick. I should have simplified this here, right? I've got the 2 there and 2 there's, so I'm going to cancel those 2 out. So minus 1 over 2x squared plus 2x delta x. And we could leave it like that, though it's hard to see, you know, it's easier to kind of combine these fractions to really see that this is an infinitesimal, because right now this is finite, right? X is a real number, so this is finite, and so is this. But we'll find that this difference truly is an infinitesimal, so it's good to complete our algebra here and put this into one fraction. So epsilon is equal to 2x squared plus 2x delta x minus 2x squared, all divided by 2x squared times 2x squared plus 2x delta x, canceling out like we need to here. So the 2x squared cancels with the negative 2x squared, and I get that this is a 2x delta x divided by, distributing through here, we get a 4x to the fourth plus 4x cubed delta x. And in the numerator, we see that this is now an infinitesimal. We can recognize it because that's an infinitesimal. And so this product is an infinitesimal. On the bottom, it's finite, but we know that an infinitesimal divided by a finite number is an infinitesimal. And if we wanted to, we could do a little bit more cancellation, right? We've got a 2x here, a 2x in this term, 2x is in that term. So if we wanted to, we could simplify and write this as delta x all over 2x cubed plus 2x squared delta x. And that's our epsilon. And we can see that it is truly just dependent on delta x and x. And so epsilon is an infinitesimal, and we've satisfied the increment theorem. And I'll write it out here at the very bottom, but we see that the change in y, we just calculated, is going to be equal to f prime delta x plus epsilon times delta x. Actually, I said I was going to write it out, but that's kind of a mess. I recommend for you in your notes, though, when you're following this, to go ahead and write that out. So to wrap up this video, I just want to kind of write down the steps we need to, that I just walked through to compute the epsilon. So for the increment theorem, I can find all these things. So one, find delta y. So delta y is equal to f of x plus delta x minus f of x. Two, we compute f prime of x. So f prime of x, we'll get some more tools on how to derive the derivative in the next few sections, but right now we're doing everything based on the formal definition. So it is the standard part of the change in y over the change in x. Then we get that the differential is, so if we just want to write it out, it's f prime of x, which we just calculated in step 2, dx. And then finally, if we want to find the epsilon, demonstrate that the incremental theorem is valid, which it will be for all these functions, we solve the equation delta y is equal to f prime of x delta x plus epsilon delta x, and the variable that we're interested in is epsilon right here. So in this work, we would subtract, divide by delta x, and find what epsilon is. And we should be able to convince ourselves, just like we did in this problem, that our epsilon is truly an infinitesimal, just like the theorem requires that it is. So we'll look at another example of computing the differential in the next video, as well as another example of finding the tangent line to a curve.